Another very important theorem is the maximum power transfer theorem. So this is one theorem which you are going to see in the other subjects as well. Okay, so it's better that you understand it well here itself. So what does this state? When you have a network, a linear network, and a load resistor. Okay, so you have a load resistor RL. Now at what value of RL? Okay, so remember, at what value of the load resistance maximum power will be delivered from this network to this resistor, to this load. Okay, so that is what the maximum power transfer theorem is going to talk about. Okay, at what value of RL can maximum power be delivered from the network to the load. Okay, sometimes what happens is they will give here network A and here network B, and what will be the power, maximum power from transferring from network A to network B. Okay, so that kind of problems also you can solve with the maximum power transfer theorem. Now this network we can represent in its Thevenin's equivalent form, right? So what will be the Thevenin's equivalent form? Resistance RTh, which is in series with the voltage source VTh. Okay, and here we have the load resistor RL. Okay, now what is the power that is delivered if you take the current flowing through the load resistor as IL? Then what will be the power delivered? Power delivered to RL is IL square into RL, and IL you can write as VTh by RTh plus RL whole square into RL. Okay, so now what is the variable quantity here? RL is the variable quantity. Now if you differentiate this with respect to RL and equate it to 0, then you are going to get the maximum value. Okay, so we are just applying the maxima minima, right? So here you can write the power delivered if you are taking as PL, this is PL, then maximum value you can get by differentiating this with respect to RL and equating it to 0. Okay, now this proof we are not going to go through in detail. The final result I am going to write. If you are interested, you can do the proof very well. Okay, so RL is equal to RTh. This is the final result. So when the load resistance is equal to the Thevenin's resistance of the network, then maximum power is going to be transferred. Okay, as simple as that. Now what will be the maximum value of power? PL max, therefore PL max is going to be equal to, this is VTh by RTh plus RL, you can write as 2 RTh, this entire square into RL, once again you can write as RTh. So what you are going to get here? VTh square by 4 RTh. This is the maximum value of power that is delivered to the load resistance. You can also note down the PL versus RL. That means as RL varies, how PL is going to vary. Okay, so this is just for an extra idea. Okay, it's not very important, but just for an extra idea. So initially as RL increases, power will increase at the peak, from then it will start reducing. Okay, so this is the value when RL is equal to RTh, and this is the PL max, which we just found as VTh square by 4 RTh. Here if you take an example, find the maximum power that can be delivered to RL. Okay, so you can see this is the RL. Now if you can take the terminals here as A and B. Now what we have to do, the only thing that we need to do here is this network we have to find the Thevenin's equivalent and then equate the load resistance to the Thevenin's equivalent. Okay, so first we will find the Thevenin's equivalent. One thing here is you can pause the video and you can do the problem by yourselves first. Okay. So I'm just redrawing the network, and now you have to keep it open circuit here, right? So this is the value that we want. Here it is 2 ohms, 2 ampere, 3 ohms, 12 ohm, 6 ohm and 12 volt. Okay. So you can apply nodal analysis here, but it is much more simpler if you can do the source transformation, right? So here you can just replace this voltage source in series with the resistance to a current source in parallel with the same resistance. Okay. So that means you're going to get 6 ohms here, and what is the value of current here? 12 divided by 6. So 2 amperes. Okay. Then next you can see that the 6 ohm and 12 ohm resistances here, they can be replaced by a single equivalent resistance. Okay. So 6 ohms in parallel to 12 ohms, you're going to get 4 ohms. Once again you can apply the source transformation so that you can replace this 2 amperes and the 4 ohm resistance into a voltage source in series with the resistance. Okay, so this will remain 4 ohms and the voltage source is going to be 2 times 4, which is 8 volt. From this circuit you can directly get VTH, okay, because there's only one entire loop here. So 2 amperes current is flowing here. Okay, so this is going to be 2 amperes. Now if you apply KVL, so let's apply KVL in the direction of the current. So this will be the direction of current, right? So the voltage, 8 volt voltage source, it is going to be plus 8. Then VTH is going to be minus VTH plus 7 times, because 3 plus 4 into 2. Okay, so this is equal to 0. So how much will you get VTH? This is 8 plus 14, which is 22 volt. So you have found out the Thevenin's equivalent voltage. One more thing is left out. What is that? You have to find the Thevenin's resistance. So this is VTH. Next we have to find RTH. Now this is the circuit. For RTH, what you have to do, you have to turn off the independent sources. So this current source, it is going to become open circuit and the voltage source is going to become short circuit. Okay, so here you're going to get short circuit. So now what is RTH? This is 2 ohms in series with 2 ohms, and this combination is in series with 6 ohm parallel to 12 ohm. Okay, so this you're going to get as 9 ohms. So now you have found VTH, you have found RTH. What is the only thing that's left out? The maximum power that is delivered. This we have already found out to be VTH square by 4 RTH. Okay, so 22 square divided by 4 into 9. So this you are going to get 13.44 watts. Here we have one very important question. At what value of RS will maximum power be delivered to load RL? Okay, and various options are given here. So the first option that you might go to is RS is equal to RL. Okay, but that is absolutely wrong. Remember that the maximum power transfer theorem was used when RL is variable, not RS. Okay, RS was fixed, then RL should be equal to RS so that maximum power will be delivered to this RL. But if there is a choice that RS can be changed, RS is variable, right? So here RS is variable. Then what you can do, the best possible would be if RS is the smallest value possible, which is nothing but 0. Okay, so why is that the case? When RS is 0, then entire 5 volts will develop across RL and the maximum power, that is the maximum power case. Any non-zero value of RS will lead to a voltage drop across RS, and the voltage drop across RL will reduce. Okay, so once voltage is reduced, then the power is what? Voltage square by the load resistance RL. Okay, so this is the important point that you need to remember here. Whenever RS is given as variable, then the ideal case is that it should be 0. So you can write the important point here: for application of maximum power transfer theorem, the load resistance RL should be variable. Okay, and what is the other condition? And the source resistance or the Thevenin's resistance should be constant. Okay, if RS or RTH is variable, then maximum power transfer will occur when RS or RTH is equal to 0. So RS means basically source resistance. So when a source is given, if its source resistance is 0, then it will be able to deliver the maximum power. Okay. RTH is the Thevenin's resistance. Okay, since they are both in the same form, Thevenin's equivalent is also a voltage source in series with the resistance. Okay, so that's why I am just writing as RS or RTH. Okay.